Okay, quick break. So now we're back and we're picking up where we left off. At this portion of the lecture, we want to be focused on recognizing ionic compounds. So essentially we need to be able to distinguish what type of compound we have. There are four types. There's the metal, non-metal. These are also known as binary ionic compounds. Then you have metal and polyatomic ion. So this is sort of like having those bigger size molecules paired with a metal. Okay, same thing. They typically have a -1 or -2 charge, and they would just pair with the metal. Then you have ammonium non-metal or ammonia polyatomic ion. Okay, so let's go back to the metal non-metal. As mentioned, these are also referred to as binary ionic compounds, and they have this notation where they have a metallic element that's paired with a non-metallic element, and the subscripts just refer to how much of each is present. So I think it's better that we take a step back to take a step forward. So let's look at the group 1 cations. So we see that the group 1 cations, these are our metals, right? So let's say we have aluminum. It has a +3 charge. This is always the case. Now, in terms of the binary compound, it only has a metal and it has a non-metal, right? So if we take our aluminum, if we were to pair aluminum with hydrogen, the subscript for hydrogen, or for the hydride anion, would be what? 3. So that would be Aln3. So it's just as simple as that. You're going to match the charges so that the overall charge on the molecule is 0. What's also important to highlight is that these are polyatomic anions. So you can take that same aluminum anion, which is a positively charged metal, and you can pair it with something like phosphate. You would only need 1 phosphate to balance the charges. But it would be different for carbonate. You would need 2 aluminum metals and 3 carbonate polyatomic anion groups to balance the charges. Okay, so we want to go into why that's the case. So we've talked about the metal and the non-metal. We talked about metal and polyatomic anions, how they come together to form those complexes. In this case, if you were to take the same aluminum cation, as you can see, they all have a +1 charge. So you would need 3 of these negatively charged polyatomic anions to balance the charge on the positively charged aluminum cation. So I think by now you're getting the gist. So don't allow the bulk of the size of these complexes to intimidate you. What's really essential is that you recognize the charge and that you use the charge to balance the charge on the metal. Okay, so we talked about metal, non-metal. We talked about metal, polyatomic. Let's go back to talk about ammonium, non-metal. So this is the ammonium anion, and it's a special type of chemistry. The ammonia can form complexes with different things. So you can have the ammonium cation, which is a polyatomic ion, and it can form the same type of complexes as a regular metal, which is monatomic. So once again, I mentioned what's only important is that you balance the charge. So this group has an overall charge of +1, and it can form a complex with an hydroxide anion. So you would have 1 ammonium group and you would have 1 hydroxide group. If you were to have a compound that has ammonium carbonate, you would have to have 2 ammonium groups, right? Because you have 2 charges on the carbonate. So that compound would be called what? Diammonium carbonate. So that's pretty much straightforward. And so now you know what ammonium nonmetal and ammonium polyatomic ion is. So the online material also gives you an opportunity to practice naming the binary covalent compounds. Let's go through a few of them just to make sure you're following along. So on this tutorial, you can select numbers between 1 through 15, and you can keep record of your progress, okay? So we're looking at group 1, at problem number 1. They give us the chemical name. We need to provide a formula. So what do we know about nitrogen? Nitrogen is non-metal, right? So it's non-metal, and we can see that it has a prefix of 2. So we can apply that 2 to the subscript. And in this case, we have a prefix pent, that means 5-oxide. So based on the name alone, we can develop a chemical formula. Let's look at a second example. So in this case, we have carbon tetrabromide. Carbon is in group 4, and it can form a +4 or a -4 ion. Since in this case we have 4 bromide, although this is non-metal, this will be forming a covalent compound with the tetrabromide. So we would need 4 bromide ions to balance the charge on the +4 carbon. But you see, carbon, its name doesn't have a Roman numeral. And you see in bromide, it has the subscript I, so you can tell that this is the anion and this is the cation. Okay, so please note here that bromine does not have the negative notation. In this complex, it would serve as a positively charged species. It may not be easy for you to grasp, but the bromine can lose 2 electrons and therefore is able to bind with 3 fluorides. And so by losing 2 electrons, it goes from having a valence shell of 7 to 5, and now it can acquire 3 electrons from each of the fluoride. You can see the fluorides are all negatively charged, okay? But to provide a chemical formula, you just need to use the information provided in the prefix. Okay, so this is just an opportunity to name the binary covalent compounds, but this is pretty easy. We should look at some examples of going from the formula to the name. So what is this? You have 1 nitrogen and you have 2 oxygens. So this would be nitrogen dioxide. So I know that it's an oxide because this is located on the right side of my chemical formula, so it must serve as my cation. Or my anion, sorry. Okay, so what is this? This represents phosphorus. This is phosphorus pentachloride. Okay, Okay, so please go through this and practice as much as needed. It's straightforward. It gives you direct feedback, and you can figure out what you know and what you don't know. Okay, so as you can see, when you're converting the ionic formulas to names, you just need to provide the name of the cation and the name of the anion. So one example would be nitrogen dioxide. Nitrogen was our cation, and the 2 oxygen atoms serves as our anions. And this is a review of how to name each cation. So if it's located in group 1 through 3, or if it's the metals aluminum, zinc, and cadmium, then you know that they only have one possible charge, so you just give the name of the metal. Other metals that aren't listed above or included in this list, they can have a possibility of having more than one charge. So you need to provide the name of the metal and a Roman numeral to indicate which charge is present on that ion. For polyatomic anions, such as ammonia, you need to just give the name of the polyatomic anion. And this is a much shorter list. For naming anions, you only have 2 options. If it's monatomic, you give the root of the nonmetal and you use the suffix "-ide. And for polyatomic anions, you just provide the name of the polyatomic anion. So once you have knowledge of the names, then you can convert the names to formulas. So it's pretty straightforward. But first you need to determine the formula, including the charge for the cation and the anion, and determine the ratio of ions that yields 0 overall charge. In order to identify the charge present on the anion or the cation, you can use this chart. So this is group 1. As mentioned before, each element in group 1 forms a +1 charged ion. In group 2, each element forms a +2 charged ion. Group 3, it all forms +3 charged ions. Some elements such as iron and copper and other transition metals, their ionic states depends on the reaction. So they're not always automatically known. Others like silver, cadmium, and zinc, and aluminum have well-known charge states. On the far right side of the periodic table, groups 5, 6, and 7 have negatively charged ions. And in group 5, you can see they all have -3 charge. And this is because in order to fill their valence electron to have the same electron configuration as the noble gas, they need to have an additional 3 electrons. So this chart is very useful. Although it doesn't provide the charges for each element, you can find a resource online, or you can just look at their location on the periodic table, and it gives you a clue to what charge each of these elements might acquire when they form ion. And this is just a review of how to label or generate a binary covalent compound. It's just like the binary ions. The difference is they're both nonmetals. So this would be an example of nitric oxide, nitrogen dioxide, those type of compounds. So these are common names for covalent polyatomic compounds. So these are binary. You have hydrogen oxide. By binary, we're saying they just have 2 different types of atoms. Water obviously has hydrogen and oxygen. There are 2 atoms of hydrogen, 1 atom of oxygen. So you can see how many of each atom are present in each of these compounds. This differs from ammonia by having 3 hydrogens instead of 4. If you add hydrogen to ammonia, you create ammonium, a positively charged anion. It's polyatomic as well. Methane has 1 carbon and 4 hydrogens. Ethane has 2 carbons and 6 hydrogens. Propane has 3 carbons and 8 hydrogens. So these are the rules for naming binary covalent compounds. It's pretty straightforward. I wouldn't be labored to read everything on the slide. I think it's sufficient to say you need to know the name of each of the elements. And you do not need to write mono on the first name if it's only one. You just need a prefix to identify the quantity of each. If the subscript for the first element is greater than 1, indicate the subscript with a prefix. Okay, it's pretty straightforward. Follow the prefix with the name of the first element in the formula. Okay? Additionally, write a prefix to indicate the subscript for the second element. Write the root of the name of the second symbol in the formula. Add I to the end of the name. So this goes back to what we just did. We can do a few examples just to make sure you're following along. So in this case, why don't we go from the chemical formula and provide a name. So these are both nonmetals. They're a binary compound. They're covalent. You only have a subscript for oxygen. So you don't need to call this mono nitrogen dioxide. If we can recognize it only has one nitrogen, so we're just going to call it nitrogen dioxide. Okay, so I think you get the gist. Maybe one more for the row. Okay, neither one has a subscript. They're both nonmetals. This is a binary covalent compound. What would you call it? I would say this is hydrogen. This is my anion, so I'm gonna call it hydrogen fluoride. Okay, so spelling is obviously important. Make sure you put the U before the O. There is no other way to spell it. So for those of you who need a review, these are the prefixes. Mono represents 1, di 2, tri 3, tetra 4, and sometimes it may not be convenient to put the A. You really only need the A there if you have like a consonant. For example, in pentoxide, you don't need to say pentaoxide, just say pentoxide. But if you had pentachloride, if you had a chloride, the consonant, you need to put the A there. And the same rules apply here. So these are common prefixes I'm sure you've come across multiple times. Okay, so small review. Root names of nonmetals: hydrogen, carb, nitrogen, phosphorus, ox. You've seen this before. So, forms of binary covalent names. These are different ways they combine. So you have the prefix for the name of a nonmetal. Then you have the prefix for the root of a name of a nonmetal, and I. So in this case, you would have a positive charged nonmetal, or it may not have a charge. And then you have a certain quantity that you indicate with the prefix. And for the nonmetal that's negative, you also have a prefix to indicate the quantity. For example, dinitrogen pentoxide. And the other option is to have the name of a nonmetal, the prefix of the root of a name of a nonmetal, and the suffix I. Okay, so that example would be carbon dioxide. And that's, I mean, you know, they're saying the same thing like 3 times, right? So, how do you write binary covalent formulas? Write the symbols for the elements in the order mentioned in the name. This is straightforward. Write subscripts indicated by the prefixes. Okay, so we've covered pretty much how to go from the chemical formula to the chemical name for not only monatomic ions, polyatomic ions, and also compounds which are not ionic but otherwise are covalent. You can have the same polyatomic ion group that's paired with a non-metal and form a covalent compound. If it's paired with a metal, it forms ionic. So keep in mind, typically metal compounds, when they pair with non-metals, they form ions, and when non-metals and non-metals pair, they form covalent bonds. And once you know each of the symbols and the quantity in terms of the subscript, you can name it with a prefix and vice versa. Okay, so we won't make this part too hard because we have other things we'd rather use our brain power on. So let's take a quick break and we'll come back.